Excess energy, in violation of the principle of conservation of energy, can be obtained when the travel along a part of the closed loop in a conservative field, such as gravitational field, is spontaneously assisted by another conservative field, such as the magnetic field, and vice versa. This is a schematic of an experiment which illustrates this violation. A steel sphere 4. Lifted from position A to B, and let go along a track 3. Sandwiched between two permanent magnets 1. Shown in solid black, completes closed loop ABCA, and goes spontaneously back to A, aided by a curved track 2. Observe that while the steel sphere is covering the closed loop ABCA in the magnetic field, it also covers the same closed loop in the gravitational field. Because of an appropriate construction, these two fields, although conservative individually, act in such a way that mutually assist each other in covering parts of the loop. Now we will make several observations that will help us understand how conservation of energy is violated. Observe first that, for the purposes of our discussion, the sphere at position A has zero gravitational potential energy. We will say a little more on that matter below. The sphere at position B has gravitational potential energy equal to mgh sub 1. The sphere at position C has zero magnetic potential energy. The sphere at position B has magnetic potential energy equal to m sub B. The imparting of gravitational potential energy starts at position A, where the gravitational potential energy of the sphere has its minimum value. The maximum imparted gravitational potential energy is at B. The sphere starts disposing of its magnetic potential energy at B, where the maximum is of the spontaneously disposable magnetic potential energy. The sphere disposes of its entire magnetic potential energy at C. This is all the magnetic potential energy which the sphere is capable of disposing of spontaneously. The minimum of the magnetic potential energy is at point C. It may seem strange that magnetic potential energy is zero where the force of magnetic attraction is the greatest, while the magnetic potential energy is non-zero, where force is lesser. This can be understood by observing that under the studied conditions, the magnetic force on the sphere, when removing it from the potential energy minimum, point C, is not constant. This is important because force determines the work done upon this removal. Work is force times distance, and with changing force, this work, unlike the work in a gravitational field, can only be determined through integration. Notice how simple it is in the gravitational case even if we apply integration. Because the force of gravity is constant for the change of height studied here, it can be factored out of the integral. The end result is just a multiplication of a constant force by changing distance. The situation with the integral for the magnetic potential energy is quite different. Because the magnitude of magnetic force changes with distance, it cannot be factored out of the integral. Thus, if one does not consider the entire integral from k to L but only ponders over the force at k and compares it with the force at L, one may remain with the wrong impression that because force at L is smaller, then also the potential energy at L is lower. The sphere at position A has gravitational potential energy with respect to the center of the Earth equal to mgh, where capital H is the distance from A to the center of the Earth. The sphere at position A has also magnetic potential energy equal to m sub A. The sphere at A also has energy of the bonds that keep together the particles that build it, energy of thermal motion and so on. And energy has also been spent to place it at A. However, in carrying out the energy balance between the input energy E sub in and the output energy E sub out, which is the goal of this study, one should be concerned only with what energy the steel sphere itself has gained and lost, not what energy other bodies or external agents have spent to impart to the sphere. As an analogy, consider estimating the gas consumption of a car for a trip from Boston to New York. The car tank may contain initially an amount of gasoline, but that amount is not taken into consideration when estimating the amount used for the trip. The energy to produce the metal for the car parts, the energy to make the parts themselves, the energy to assemble them or energy spent to bring the car to Boston is also not included when estimating the amount of gasoline used for the trip from Boston to New York. The sphere in B has energy m sub B plus mgh sub 1. Now that we know that the starting combined gravitational and magnetic potential energy at A is 0, we can appreciate that lifting of the sphere from A to B requires the imparting of energy to the sphere of the amount of E sub in equal to mgh sub 1 minus the difference of the magnetic potential energy of the sphere at A and B. Notice, now we consider the value of the magnetic potential energy in A, because we now need to know what its change is when displacing the sphere to B. We did the same for the gravitational energy at A. The combined gravitational and magnetic potential energy E sub A in A is taken as 0, but the change of energy the body experiences when moved from A and placed in B is not 0. Recall the analogy with the car getting from Boston to New York and how the expenditure of gas for that trip is calculated. Now, something amazing is observed. Lifting of the sphere from A to B requires the imparting of energy to the sphere of the amount of E sub in. Spending that E sub in causes the sphere in B to find itself with much greater disposable combined gravitational and magnetic potential energy E sub B than the imparted energy E sub in. This combined energy is energy that the sphere can spontaneously dispose of. That ability of the sphere to dispose of the energy E sub B makes up for the fundamental difference between E sub B and E sub A, the latter allowing no disposal, and therefore being taken as the initial state 0. Conservation of energy is violated. When placed at B and let go, the steel sphere travels along BCA and not directly along BA route. Now, the most important thing to understand is that along this path of return, also, the entire amount of energy mgh sub 1 plus m sub B the sphere has at B, available to be spontaneously discharged upon the return of the sphere to A, is, indeed, lost by the sphere altogether. All of it. Back in A, after completing the ABCA loop, the sphere will have no energy whatsoever which it can lose spontaneously, and will recover its initial state with E sub A. equal to 0, as already explained. Again, back in A, the sphere will have energy of thermal motion, energy of the chemical bonds, gravitational potential energy with respect to the center of the Earth, magnetic potential energy m sub A, with respect to C, etc. But none of these energies can be transformed into other kinds of energies spontaneously. Indeed, when traveling from B to C, sphere loses spontaneously magnetic potential energy m sub B minus 0, which has to be subtracted from mgh sub 1 plus m sub B. Then, upon its return to A, the sphere will also lose the gravitational potential energy, mgh sub 1, and will be left with E sub A, equal to 0. However, reaching the initial state A, with E sub A equal to 0, by completing the ABCA loop, was achieved by the sphere losing energy out, which is greater than input energy in clear violation of conservation of energy. The whole exercise shows that when there is a field, all the potentialities are there to produce excess energy, only with a slight impetus, provided the proper constraints are assured, which we call proper construction. The results presented above show for the first time a hitherto unrecognized possibility for violating conservation of energy. Violation of energy conservation in electric and electrochemical systems is demonstrated elsewhere. All demonstrated possibilities to violate conservation of energy make it impossible to consider the principle of energy conservation as a universal principle anymore, and the latter must from now on be considered as only an exception. This discovery of the unrecognized so far inherent possibility to violate conservation of energy opens unforeseen far-reaching perspectives for the building of principally new energy generators, as well as an ideological change in all of science, which is probably of even greater importance than the pure utilitarian applications of the discovery at hand.